Now that we've studied the Schrödinger's equation and we learned how to extract information from the solution to the Schrödinger's equation, which is psi, and we even linked the Schrödinger's equation to Newton's second law, we did learn a lot about the general idea of Schrödinger's equation. But the primary function of Schrödinger's equation is for us to solve for the wave function given a certain potential. So now we're going to take a look at how to solve Schrödinger's equation given a specific potential. For simplicity, we start with one dimension. Let's look at some examples of Schrödinger's equation in one dimension. Later on, we're going to extend this one dimension to three-dimensional cases. And we're going to separate our solutions, our situations, into two general categories, the so-called bound state A or scattering state B. A bound state, here is an example of bound state. You have a potential that looks like this, and it's lower in the middle and it's higher at the two ends, and we call it the potential well. And the energy of this particle is fixed. I'm assuming it's a stationary state, therefore the potential energy doesn't act as a function of time, and the energy therefore is conserved, and this energy is lower than the value of the potential at the two edges when x approaches positive, negative, infinity. Now, when energy is lower than potential energy, classically we know the particle cannot get there, right? In quantum mechanics, things are not that simple, but still, when you have a very tall potential and lower total energy, you can imagine the particle cannot possibly go to positive, negative, infinity, and therefore it is trapped in a finite region in space. And we call this a bound state. It is bound somewhere between here and there. The second case is called scattering state, and that is when the potential is lower than the energy of the system, even at x equal to positive and negative infinity. So therefore, the particle is able to go to positive and negative infinity. You cannot trap this particle in a finite region in space. It is not a bound state. We call it a scattering state. We're going to solve these two types of questions separately, and in particular, we will be, for the first time, answering this question. Why is energy quantized in quantum mechanics? You know, Planck's quantum hypothesis was very convenient. It worked out quite well for a number of phenomena, so it was very successful. But Planck himself never answered this question. Why is the energy of the photon quantized? In other words, what does quantization come from? And as a related question, is it always quantized? Is energy always quantized? You might think that the reason why we call it quantum mechanics is because everything's quantized. Well, we're going to take a closer look at the condition of quantization, and it turns out this is nothing you can take for granted. This is something we can derive naturally by solving the Schrödinger's equation, whether energy is quantized or not. Our first example is really a simple case. It's called a particle in a box. This is our first example of bound state, A1. It is otherwise known as one-dimensional infinite potential well, or one-dimensional infinite square well. It sounds fancy, but what really is that this particle is trapped in between a region between here and there by very high potential walls, so that the potential energy is equal to infinity outside these two walls and 0 inside. Of course, nothing can live in a potential of infinity, therefore the particle must be trapped between here and there. And we typically choose a coordinate system which starts from the left edge of the potential well, so that's x equal to 0, and the right edge where x equals L, L being the length, the width of this potential well. It's infinite potential well because the height of the two potential walls on either side is infinity. So this is called one-dimensional infinite potential well. It's also particle in a box because the particle is trapped in the box of finite length L. Classically, we can imagine what happens if you put a particle in a box like this. So once it's inside the box, it's subject to no force, so it keeps on going at a constant rate. And once it reaches here, it can no place to go because it cannot penetrate through the wall, which is infinitely rigid, so therefore it bounces back. So it goes back and forth, back and forth, back and forth. Now, in quantum mechanics, a particle moving at a fixed momentum from here to there actually is described by a wave, a simple harmonic wave. right? So you have a simple harmonic of going this way, and then you have another simple harmonic going backwards. So you got two waves, one going this way, one going that way. The result, as you know, is a standing wave. So we can expect the solution to the wave function to be a standing wave. So once again, this is the potential energy curve. Infinity from here on, and from there on, and 0 in between 0 and L. Here is the Schrödinger's equation written down for this problem, negative h bar squared over 2m, second derivative psi, that's the kinetic energy term, plus u psi equals e psi, and u is, again, infinity and 0, depending where it is. How do we solve this type of problem? Well, this type of problem is called a piecewise constant potential. What does that mean? It means the potential energy is not an overall constant in all of space, but when you separate the space into different pieces, this piece, this piece, this piece, or different regions, then in every region, the potential is a constant. For example, in this region, it is a constant which is equal to 0. It's called piecewise constant potential. And let's say how we can solve this piecewise constant potential problem, the Schrödinger's equation. I have rewritten the Schrödinger's equation by moving this u term to that side. Now, u is a constant in a given region. So E, of course, is also a constant, so E minus u is a constant. And I'm now moving 2m over there and h bar squared down there. So I get this combination, okay? 2m times E minus u over h bar. This whole thing must be a constant in a given region. When you go to a different region, u changes, you get a different constant. But for every region, you have a given constant. That constant may be positive or negative, depending on whether E is greater than u or E is less than u. If E is greater than u, that constant is positive. Because it's positive, I give it a name. I call it k squared. Okay? And if E is if E is greater than u here. If E is less than u, that constant is negative, and I'm going to call it negative kappa squared. Kappa is a positive constant, but you have a negative number in front of that. So you have two distinct type of solutions, depending on whether E is greater than u or E is less than u. In our case, we have two regions. One is outside the box, one is inside the box. Outside the box, don't worry about it. We don't have to solve it. What is psi equal to? Psi represents the chance of the particle being in a certain region, and outside, the particle cannot get there because u is infinity. There's a psi just equal to 0, right? Psi equal to 0, so don't worry about it. There is no chance the particle ever gets out. We only have to worry about the particle inside the box. And inside the box, what is u equal to? 0. Okay, so therefore, E minus u is positive, so we choose this, k squared. Therefore, I'm going to call this k squared. Define as k squared. And what is the corresponding Schrödinger's equation inside the box then? So this is the Schrödinger's equation. Second derivative equals negative k squared times psi. And we have seen differential equations like that. In fact, even in physics itself, we saw it in 1b. That, in fact, is the differential equation related to simple harmonic motion, except this x is t. The solution, nevertheless, has the same general form. It's a sine or cosine function, right? So here's our most general solution for the wave function inside the box. It's a sine or cosine function, and that's a standing wave as expected. And I'm writing down here the most general possibility of the wave inside for 0 less than x less than L. A sine kx minus plus b cosine kx. You plug that in, you find the two sides are equal to each other. What is A, what is B, what is K? I have no idea yet. So what do I do next? I have to find A, I have to find B, I have to find K, right, in order to solve this entire thing. Now, the trick I use here is the so-called boundary condition. Boundary condition. This is of great importance. What is boundary condition? And that is what happens to the wave function at the edge of the solution. This solution is only valid between 0 and L. So the boundary, there are two boundaries. One is x equal to 0, the other is x equals to L. At x equal to 0, what should the wave function be? At x equals L, what should the wave function be? These are called boundary conditions. And in our case, right outside the edge, the the field, the wave function goes down to 0, right? So what happens here? The wave function has to be 0. You know, the wave function cannot be 0 right outside and then non-zero right inside, which means the wave function will have to jump between one value to another value. It's discontinuous, and physically that makes no sense, because that means the particle, when it's very close to the edge, doesn't know what to do, whether it has a finite chance to be here or 0 chance. And therefore the wave function has to be continuous in order to be physically meaningful. The wave function has to be 0 here and there. So when you plug in x equal to 0 into this general solution, what will you be getting? 0. Okay, psi should be 0. That clearly rules out the cosine function, because the sine function does go to 0, but the cosine function doesn't at x equal to 0. So that tells me the cosine function is gone. You're left only with the sine function, sine kx. But don't forget, I have the other boundary condition. That's what happens at x equals L. Psi should also be 0. So again, psi 0 equal to 0, that means b equal to 0. So don't have the cosine function. And psi L has to be equal to 0 as well. But psi L is a sine KL, right? If you plug in x equals L. And that is equal to 0. That means this k times L, which is the argument of the sine function, cannot be just anything. It must be equal to an integral multiple of pi. That's how you guarantee sine KL equal to 0. And that n is an integer, 1, 2, 3. So you see, I have arrived at a quantization condition. It will tell you what the allowed value of k has to be. And k is related to the energy. See that? K squared equal to this. So if k is quantized because of the boundary condition, then so is the energy E. We have therefore arrived for the first time the quantization of energy through a strict derivation, not just an artificially imposed quantization condition. So where does quantization come from? In this case, at least, it comes from the fact that we must satisfy the wave function's boundary condition. It is a matter of solving the Schrödinger's equation and satisfying the boundary condition. It will give you the quantization condition itself. You do not have to artificially impose on it anymore. So you work out k from this expression, from this quantization condition. K is n pi over L. And you know, k is related to the wavelengths of the wave by 2 pi over lambda, and therefore lambda equals 2 pi over k, and k is given by n pi over L. You solve this, you can find L. L can be expressed in terms of the wavelengths of the wave, and it turns out L equals n times lambda over 2. This sounds very familiar. If you recall from physics 1b, we learned that same exact formula for standing waves on a string. Standing wave on a string. And what is lambda over 2? That is the length of a loop. So that tells me that within this region between here and there, I can only fit an integer number of loops. Say, for example, 2 loops, 3 loops. Here is an example of 3 loops. That's n equal to 3, and so on. You can only fit an integer number of loops. In 1b, that was because the 2 ends of the string must be fixed. So the amplitude of the oscillation must be 0 here and there. Here we have something very analogous. We don't have a string, but we have the wave function. The wave function must go to 0, just like the amplitude of oscillation of the string must go to 0, and therefore, by the same argument, you can only fit an integer number of loops of the wave function in between. Okay, it's a standing wave with a number of loops. That number must be an integer. That gives us the quantization of the wave vector k, which in turn gives us the quantization of energy. So, I have the following wave function. This is the wave function of the nth quantized energy state. N equal to 1, 2, 3, and so on. A sine kx, k is n pi over L. I have here n equal to 1, 2, 3, and so on. As you can see here, the greater the number n, the more number of oscillations I have. Here's 1 loop, 2 loops, 3 loops, and so on. Just like the classical case of wave on a string, except we have a new physical meaning for these waves. These are material waves representing the particle's probability. In fact, the probability density goes like psi squared, right? So here is psi squared. You take this first, the lowest energy wave when n equal to 1. You square it, you get this. And here's n equal to 2, n equal to 3. How do you interpret this kind of curve? This represents, again, the probability density of finding the particle. So you see the probability density is 0 at the two edges and gradually goes up. So this means that at n equal to 1, the particle is more likely to be found somewhere in the middle, less likely to be found near here. And when n equal to 2, you have a double hump. What that means is that the particle is very likely to be found here and here, but the chance of finding the particle in the middle is what? It's 0. Here and n equal to 3, you have 3 humps, so the particle is more likely to be found here, here, here. These are actually antinodes for the wave, and it's impossible to find the particle here, 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 and here. These are nodes. So again, the math is very much the same as standing wave on the string, except the wave is a probability wave. So what about energy quantization? Well, we know k squared is related to energy like this. That's how we define k. And inside the box, u equal to 0, so you don't have to worry about that. You then solve for E in terms of k. It's h bar squared k squared over 2m. Now that makes perfect sense because h bar k is just the momentum, right? P. So it's just p squared over 2m. The kinetic energy, no potential energy inside the box. And k is, again, itself equal to 8 mx over L as we just derived. And we rewrite this by taking the n squared out. You're left with this constant, h squared over 8mL squared, which has the unit of energy. The energy of the system, E in the nth quantized state, must equal to this expression times n squared. In fact, this expression is the energy value when n equals 1, because n squared is 1 as well. So this is E1, and the total energy of the system in any quantum state must be equal to this E1 value times n squared. It cannot be just anything else. And n is 1, 2, 3, 4, and so on. You see, energy is indeed quantized. And as another example of numerical estimation, we can figure out what roughly E1 is, given some reasonable numbers. E1 is h squared over 8mL squared. And if I want to estimate that, I have to be given a value of m and L. So let's say we put an electron inside. So mc squared is equal to 511 keV for an electron. And let's say L is the size of an atom, roughly, which is 0.1 nanometers. The same trick applies when you do the numerical estimation. I'm going to multiply both numerator and denominator by what? By c squared. So this I get hc squared. And here, I have, instead of m, I get mc squared, which is equal to 511 keV. Now, hc, again, is 1240 eV nanometers, as we know. You square that, divided by eV, and nanometer squared. So nanometer squared cancels nicely. You're left with only eV. That's a simple way of calculating it. And the answer is about 150 eV. Don't take that number too seriously. Again, it's only an order of magnitude estimation. So basically that tells me you trap an electron inside a one-dimensional box whose length is about the size of an atom. The particle inside that box must have at least this much energy, about 150 eV. It cannot have an energy of 0, because if it has energy of 0, then it's not moving. When it's not moving, the momentum is 0, so there is no error in the estimation, in the calculation of momentum, because it's 0. But on the other hand, delta x is not infinity. It is in fact about L, because it's trapped inside the box, right? So then you have delta p times delta x, which is 0. That violates what? The Heisenberg uncertainty principle. So it's got no choice, but it has to move. In fact, the smaller the size of the box you put this electron in, the greater the E1 is. We did something similar previously when we considered the atomic energy versus nuclear energy in the Heisenberg uncertainty principle, right? We got a similar idea. You put a particle in a much smaller confinement, you get greater amount of energy, and this is an exact measurement of the energy of a particle in a one-dimensional box. And again, we see this qualitative idea. The smaller the box that you put the particle in, the greater its kinetic energy has to be. And that is a direct, there is a direct link to the uncertainty principle. So now we plot what's called energy spectrum, okay? Or energy level diagram is the same thing. These are called energy levels because level means it's discrete, okay? It's in steps. E1, E2, E3, and E4. E equal to 0 is right here, and the particle cannot be at E equal to 0 as we just mentioned before. This is the lowest energy it can possibly have, E1. The next one is 2 squared times E1, that's 4E1. The next one is 3 squared times E1, and it's 4 squared times E1, and so on. And the energy gap, as you know, increases. This is the lowest possible energy the particle sits in. We call it the ground state. Ground state energy. This is the level that's right above the ground state. We call it the first excited state. And what about this one? That is called the second excited state. Okay, and so on. So the ground state energy of the particle is E1, and the first excited state energy is 4E1, and followed by the second excited state, which is 9E1, and so on. This, again, this diagram is called energy level diagram. Now, when we solved Schrödinger's equation, we were focusing our attention on the value of K, and which led to energy quantization, but we left out something, and that is there's an overall constant in front of that expression for the Schrödinger, for the solution. The solution, again, I'm write it down here, psi n equals a sine n pi x over L inside the box, remember? This a is this constant, and this constant, whatever that is, the Schrödinger's equation is always satisfied because the Schrödinger's equation is a linear equation for psi. So you add a constant to psi, it's going to just cancel out, drop out. It doesn't really matter. It doesn't mean this a is an arbitrary number because we must satisfy the normalization condition. And what is that? That is to say that the probability of finding this particle everywhere in space must be equal to 1. Since we're dealing with the x-axis only, that means when you integrate the probability density, psi n squared, from negative to positive infinity, what do you think you'll be getting? 1, right? This tells us what this a has to be. Now, I didn't really realize that a may or may not depend on n. It could depend on n. So in general, we call it a of n. I don't want to be too ambitious by telling myself that a has nothing to do with n. I don't know. So squared, sine squared. You notice this is a real function. So the complex conjugate is of psi just itself. So just square it, dx equal to 1. All you have to do now is to solve for this integral. So an equals to, work it out. So you take the integral raised to the power negative 1/2. That'll give you an, the normalization constant. So what is that equal to? Now you can do this calculation yourself, but there is a simple trick that you can apply to solve this integral very quickly, and that is between 0 and L. The sine squared and cosine squared function, of course, they're not equal to each other, but when you integrate either sine squared or cosine squared between 0 and L with the same argument, because of the periodicity, what do you think? The integrals are the same, right? Sine squared integral and cosine squared integral between 0 and L. But when you add these two integrals up, the integrand becomes sine squared plus cosine squared. And what is that? That is just 1, isn't it? So when you replace the integrand with 1, the integral goes from 0 to L dx. The answer is just L, right? So each integral, sine squared or cosine squared, is half of that, which is 1/2. So this is actually 1/2 times L. Okay, because the total integral we replace by 1 is L, so each is half of L. Raised to the power 1/2, that's square root of 2 over L. That is the normalization constant in front of it. So now we have the complete picture. We have the normalized wave function for the nth eigenstate of energy. If the wave function equals this, then we say the particle is in its nth eigenstate of energy. The energy in this particular state has only one value, and that is E of n. Psi n, the wave function, equals 0 outside the well, and inside the well, it is equal to this. Then this constant ensures the normalization condition. Now, when we discussed in the previous lecture, when we discussed how to find the expectation value of any observable, we expanded the wave function in the in terms of the eigenfunctions or eigenwave functions of this observable. And we learned at that time, without proof, that there is something called orthogonality. And that is, if you take any observable A, and you write a whole bunch of its eigenfunctions, or eigenstate wave functions. They have different quantum numbers, m and n. And it turns out if the quantum numbers are not equal to each other, so you're looking at psi mx and psi nx, and m and n are not equal to each other, they are both eigenfunctions of a particular, of the same particular observable. In this case is energy E, because these are the eigenfunctions of energy, or Hamiltonian, right? Then we learned that if m is not equal to n, then the integral should be equal to 0. That is called orthogonality. So this wave and that wave, they're orthogonal to each other. In this case, that would require the following integral to be 0. Sine m pi x over L times sine n pi x equal to L over L. Integrating between 0 and L. It has to equal to 0, otherwise our condition would be violated. Now we never proved that condition. But I said, trust me, it's true. Now here we have a first test. Is this equal to 0? I'm going to leave this as a mathematical exercise for you. Sine n pi x over L times sine n pi x over L. It turns out if m and n are both integers, but they're not equal to each other, you can show for yourself. After you work out this integral, you actually do get 0. Okay, please work on that and show, at least for this particular case, the orthogonality condition is satisfied. You know, we learned that if we're given the wave function, then we can solve for the expectation value of anything we want to know. And here we have some further examples using our one-dimensional infinite square well. Let's look at the ground state of the infinite square well in one dimension. Given the wave function, which you already know, can we calculate the expectation values of the following two quantities, x and px? Can we do that? Well, even before we do the calculation, we sort of know what these values should be, right? What is the mean value of x? Well, the wave function, the ground state, looks like this. It is totally symmetrical. And you square it, you get probability density is also symmetrical like this, right? And therefore, what is the average or mean position of this particle between here and there? Well, clearly, by symmetry, it should be in the middle, which means the expectation value of x should be what? Half of L, right, between here and there, right? And what about px? Well, that is the expectation value of the momentum. Well, you know that this wave, the standing wave, is actually made of two waves, one going this way, one going that way, of equal amplitude. If you go this way, px is positive. You go that way, px is negative, and they have equal chance of appearing. That's how you get the sine function. And as a result, you got 50% positive p, 50% negative p. The mean value should be 0, right? So we expect this to be half of L and that to be 0. That's by common sense. But does that agree with the calculation, which we'll do in the next minute? Well, here's the calculation. With any mean value calculation, you always do this. You take psi star, and then you use this operator for that particular observable, and then you multiply by psi. Now this observable is just x itself, so it's not really an operator, so it's just x itself. So let's do this integral. Sine pi x over L, that's the ground state wave function. Sine pi x over L, and x is in the middle. And this 2 over L is just the product of the two normalization constants. Is this integral equal to L over 2, as we should expect? Well, let's see. This integral is just x times sine squared, right? Now, at this point, I can certainly leave this to you to finish the integral. It's not that hard to do. But this integral is interesting because there is an easier way to do it without actually having to solve this integral rigorously. We can just observe the symmetry of this wave function, and let's say, okay, I'm going to move the coordinate from here to there. So let me introduce a new coordinate system, which is called x prime. X prime starts from the middle of the well, not from one edge of the well. So clearly, x prime equals x minus L over 2, this L over 2, right? With that, I want you to show that this integral equals L squared over 4, so that L squared over 4 times 2 over L will give you L over 2 for the mean value of the position of the particle as expected to be in the middle of the well. Can I show that? Yes, I can. You let x prime to be x minus L over 2. Now x prime goes from negative half of L to positive half of L, right? Because the 0 point is in the middle, right? So you move from x to x prime, so x becomes x prime plus L over 2, And here you place x as x prime plus L over 2. This sign becomes cosine if you did that. Okay, clearly, if you go to here, it starts from the highest point, not from 0, so it's a cosine function, right? And again, x prime goes from negative half of L to positive half of L. Now, you break it down into two integrals. Here's the first integral. Here's the second integral. Look at the first integral. X prime times cosine. Now, this cosine function is an even function. Cosine squared is also an even function. But x prime is an odd function, right? So therefore, this entire integrand is an odd function. And when you integrate the odd function between here and there with 0 in the middle, what do you get? You just get 0, don't you? So the first integral is 0. Okay? The second integral is not 0, but it's easy to calculate. Look, what is this? What is this integral equal to? The same old trick that we simply already used a minute ago. If you replace the cosine squared function with the sine squared function, and you integrate between here and there, you're going to get the same thing, right? Because of symmetry. And you add these two integrals up, then cosine squared plus sine squared, integrand becomes 1. When integrand becomes 1, the integral itself is what? It's just L. Okay, it's not 1, it's L, okay, because you have to integrate from here to there. Therefore, each integral is half of L. So this is half of L times L over 2. The answer is L squared over 4. As we suspected. You plug the L squared over 4 into here, multiply 2 over L, you get x bar to be equal to L over 2. Exactly as we expected. So this formula that we derived for the calculation of expectation value works quite well in our simple case. And next, we can calculate the expectation value of Px in the ground state. And we do expect to be 1. Let's see if that's the case. I'm sorry, expect to be 0, okay? So here we go. The expectation value of Px, by definition, you have to introduce the differential operator for Px and integrate. And the integration goes from 0 to L because that's the only region where the psi is not equal to 0. And so you have to, there's a negative IH bar coming out, and ddx, that's part of the differential operator, right? Now, ddx of sine x, then dx. Isn't that just d of sine x, right? So the integrand is sine x, and you have d of sine x. So you call this u, this is u. So this is really u du, isn't it? So the answer is 1/2 u squared, u being the sine function. And integrate between 0 and L. But the sine function is the same at x equal to 0, at x equal to L. They're both equal to 0. So therefore, you get 0. Whether you use the calculation or you use common sense, you'll find that the mean value or the expectation value of the ground state linear momentum is equal to 0. That's expected. Now, before we end our discussion of the infinite square well, let's take a look at the uncertainty principle. The uncertainty principle. The uncertainty principle should apply to this case. Delta Px times delta x should be greater or equal to half of h bar, right? But is that really true? Does that make sense in our case? Well, I've heard an argument before, and it really puzzled me at the time. Let's see if it puzzles you. Okay, somebody has argued about this. He says, look, you have a fixed energy, don't you? Right? Because E1, E2, all these are fixed energy. Let's say we have E1 in this case. The thing is in the ground state. E is fixed, and there is no potential energy. U is equal to 0 inside the well. So the energy is just kinetic energy, right? So if the energy is fixed, so is the kinetic energy. When the kinetic energy is fixed, so is the momentum, because K equals Px squared over 2m. You fix the kinetic energy, you have to fix the momentum. And when you fix the momentum, then isn't it true that delta Px equal to 0? So there is no error in the measured momentum. But meanwhile, delta x is not infinity. Delta x is about L because the particle is trapped inside a width of L, right? It's not infinity. So when you multiply delta Px and delta x, you get 0 times the finite number, don't you get 0? That seemed to have violated the Heisenberg uncertainty principle, which says this product can never be less than h bar over 2. So that was the puzzle. That was the paradox. How did it manage to violate the Heisenberg uncertainty principle? Or did it really violate the Heisenberg uncertainty principle? At this point, I would encourage you to stop this video for a moment and think about it yourself. Do you have an answer for that? You think about it. Okay? Was there something wrong with the argument that I just made? If everything was right, then we have just violated the Heisenberg uncertainty principle. So there must be something wrong with what I said, right? What did I say was wrong? After you think about it, let's continue this video and let's solve this puzzle together. So what is the solution to this puzzle? Well, the argument was quite accurate except for one thing here. When you go from E to K, E is equal to K, which is correct. But when you go from K to P, you say when K is precisely known, and therefore P must be precisely known. That has a problem. Because K goes like P squared. It only tells me P squared is fixed. It doesn't tell me P is fixed, because P can have a positive and negative number. As long as the magnitude is the same, it's got the same P squared, okay? Therefore, you should allow for the possibility of a wave going this way and going that way. In fact, that is exactly the case. You have a standing wave, which is made of two traveling waves, one going this way, one going that way. They have the same magnitude of the momentum, but they carry an opposite direction of propagation. Therefore, the value of Px is not fixed. It's sometimes positive, sometimes negative. You do not know whether the next measurement will give you positive or negative. Only E, which goes like P squared, is fixed. Okay, P is not a single value measurement. It's a two-value measurement. Delta Px is not equal to 0. That was the hole in my argument. But it did puzzle me a lot before I realized that. Now, more precisely, we recall the definition of delta x and delta p. We did that when we introduced the most general definition of the uncertainty principle, okay, in the earlier part of this lecture. Here is how we define delta x, the RMS value, and delta px, the RMS value. We have four average values to calculate: x squared average, x average, px squared average, and px average. And out of these four, I already know two. X bar is L over 2 for the ground state. We already calculate that. Px bar is 0, okay? And what about Px squared? We didn't calculate that, but that's simple. Because Px squared is proportional to energy. Okay? Energy. And the energy is fixed. There is no, you don't have to calculate expected value or anything. It's always the same thing. And therefore, Px is also fixed. It is just 2m times E1. What is E1? E1 is h bar, I'm sorry, h squared over 8ml squared. So therefore, Px squared has a single possible value, which is h squared over 4l squared. Of course, the expected value is the same as that. No matter when you measure it, you always get the same thing for Px squared. The only thing that we did not calculate yet is x squared, the mean value. To do so, you have to actually do this calculation. Okay, I'm not going to go through the calculation with you again. It's a matter of doing this integral, and it's the assignment number, problem number 51. And here is the answer that you get if you did this calculation for the ground state. It takes a little bit of effort, but you can do it. Okay, now I have delta x equals to x squared, which is this, minus x bar squared. X bar is L over 2. So you do this calculation, there's some 1 over 3, 1 over 2 pi squared, whatever. You combine all these constants, you get 0.18076 L, roughly. Now, meanwhile, what is delta px? Well, you have px squared, which is this, and then you have px, mean value squared, which is 0 squared. So you can find delta px, right? It's just this thing squared, square root, and which is h over 2l. So now, let us multiply delta px and delta x together for the ground state of the infinite square well. And I have this for delta x, and that for delta p, and I get 0.0904h. And how does that compare with the lowest possible value allowed by the uncertainty principle? The lowest possible value is h bar over 2, which is h over 4 pi. And this number is in fact greater than 1 over 4 pi. 1 over 4 pi is 0.0796. So indeed, we did not violate the Heisenberg uncertainty principle after all. The product is somewhat greater than h bar over 2 for the ground state of the infinite square well. In the next lecture, we're going to continue with some more examples of one-dimensional Schrödinger's equation. We look into more complicated solutions, such as the finite well. If the well doesn't have infinite depth, We also take a look at the one-dimensional quantum oscillator. That is, what if a particle is trapped inside and a simple harmonic potential that goes like x squared? We'll see what happens.